So we've looked at how the motion of a particle moving in a potential of half kx square form looks like. It looks like something like cosine omega 0 t plus phi. The corresponding velocity is minus omega 0 a sine omega 0 t plus phi, and the acceleration is exactly in the opposite direction of the displacement, minus omega naught square x t, which is minus omega naught square a cosine of omega 0 t plus phi. Let me now focus a bit on this quantity omega naught plus phi, which is known as the phase of the oscillation. You can see that the motion finally, or the constants of motion a and phi, depend on the initial conditions. So phi is known as phase constant, and depending on the phase constant, the motion is different with respect to t. For example, let us take the case of phi is equal to 0. In that case, xt would look like a cosine of omega 0 t, and if plotted against t, the motion looks like this. Xt goes back and forth, starts from the maximum, goes down to equilibrium point and oscillates back and forth. What happens in the case when phi is greater than 0? If phi is greater than 0, and let us first take the case of it being less than pi by 2. In that case, the motion starts at t equal to 0 such that it would have already achieved a phase that it had at a little later time in the case of phi being 0. And in that case, therefore, the motion starts something like from this point like this. This is a case of phi being greater than 0 but less than pi by 2. What about the case when phi is greater than 0 or greater than pi by 2 and less than pi? In that case also, the motion would start at t equal to 0 as if with the displacement that it would have achieved at a later time, but for phase greater than pi by 2. This is phase greater than pi by 2, so motion starts somewhere here. So in that case, the motion would look something like this. You can see in the initial phase how the motion depends. Let us look at the case when phi is less than 0. So that xt, which is equal to a cosine of omega 0 t plus phi, would be such that if I were to take the case of phi is equal to 0, the motion would catch up. It will achieve the phase which it had at 0 at a slightly later time. So let us plot the case of phi less than 0. It would look something like this. The motion is such that it is achieving the phase which it had at 0 time, in this case phi equal to 0 case, slightly later. If I keep increasing the phase, this would be something like this, and so on. What about if I keep decreasing the phase and go to the limit of phi is equal to minus 180 degrees? How would the motion look? And how does that compare with the motion phi equal to plus 180 degrees? Let us see these two extreme cases. This is phi equal to 0. Let us take the case of phi equals 180 degrees. Phi equals to 180 degrees would be such that it would achieve at 0 what the 0 phase had at 180 degrees. So the motion would look something like this. What about the case of phi minus 180 degrees? It would catch up with the phase at 0 with 180 degree, catch up with the phase at 0 at a time which is given by this distance. So therefore this would shift here. So minus 180 degrees also would look something like this. So you see the phases 180 degrees and minus 180 degrees mean one and the same thing. Therefore, in describing the motion, it is best to keep phi limited between 0 degrees and 180 degrees. Now let us look at a nice geometric way of looking at the oscillatory motion. And this is based on the fact that when I write xt is equal to a cosine of omega 0 t plus phi, what I am really doing is representing the x component of a radius equal to a, which is rotating in this direction at speed omega 0. I am taking its x component, and this x component is really describing the motion xt is equal to a cosine of omega 0 t. So Phasor diagram is a way of looking at this motion, and it becomes particularly useful when 2 or 3 motions are superimposed on each other. But right now let us look at the Phasor diagram for one motion only. So if I have xt is equal to a cosine of omega 0 t, the initial position of the vector would be given like this, and it would be rotating counterclockwise with speed omega 0 t, omega 0, so that in time t it covers a distance of omega 0 t. On the other hand, if I had phi greater than 0, then it would start with an initial position which is given by phi, and then would be rotating with speed omega 0. Third possibility is phi less than 0, and then it would be starting from here and would be rotating like this. Its projection on the x-axis would give me the displacement as a function of time. As I said earlier, I can choose the phase to be either between 0 and 180 degrees or between minus 90 and 90. It's one and the same thing. Let us then look at the earlier example of a spring mass system where we had 4 initial situations which were different. One was that we stretched the spring to a maximum and let go. In that case, the motion would be represented on the Phasor diagram with Phasor starting from here and going around like this. The second situation was when we had given an initial positive velocity to the mass to the right, so that in that case Phasor would be here and it would be rotating like this. You can see in this case xt would look like the amplitude, which is the radius of the Phasor, cosine of omega 0 t. In this case you can see xt would look like, because after time t it will be here, so this projection would be sine omega t, a sine of omega 0 t. What about the case in which we pulled it to a distance and then gave it a velocity going this way? So the particle was displaced positively. The phasor tip has to be on the right hand side of this line, and it was moving in the negative direction. So the phasor would be somewhere here, with this angle being phi. You can see that xt is going to be a cosine of omega t plus phi, with phi being greater than 0. On the other hand, if we took this spring mass system, stretched it a bit and then gave it a velocity in the right, the particle is moving to the right and it is displaced in the right direction, it will be somewhere here and would be moving like this. xt would be a cosine of omega t minus phi, with this angle being phi. So this is a way of representing the displacement in phasor or vector way. Since x dot t is given as minus omega naught sine omega naught t plus phi, and x double dot t is given as minus omega 0 square a cosine of omega 0 t plus phi. If I represent the displacement, velocity and the acceleration on the phasor diagram, if the displacement at any given time is like this, you can easily see that the velocity phasor would be pointing in this direction at 90 degrees to the displacement. And similarly, acceleration would be pointing in the direction opposite to the displacement, 90 degrees this way. You can work it out yourself and see it satisfies all the conditions or all the directions and magnitudes, everything correctly with this representation. Finally, to sum up this introduction to harmonic oscillator, let me talk about energy in a harmonic oscillator. Energy for any system is given as 1/2 mx dot square, which is the kinetic energy, plus 1/2 kx square, which is the potential energy, which in this case would become 1/2 m omega 0 square a square sine square omega 0 t plus phi, plus 1/2 k a square cosine square omega 0 t plus phi. However, omega 0 square is equal to k over m, and therefore when I add it up and substitute and add it up, I get E is equal to 1/2 k a square sine square omega 0 t plus phi plus cosine square omega 0 t plus phi, which is 1/2 k a square. So the total energy of the system at any given time is going to be equal to 1/2 k a square, which is sensible. If I displace the mass to its maximum displacement, then the velocity is 0, and therefore all the energy is potential energy, which is equal to 1/2 k a square. Let us see it graphically. If I were to plot xt, let us take the case of a simple motion where phi is taken to be 0, then xt would look like this. If I square it, x square would be a square cosine square omega t, which is all positive. It will start from here, go down, go like this, and so on. Notice that here it is less than the displacement curve. The square of 1 is the square of quantity less than 1 is less than 1. Similarly, x dot, let me show this with red, square would look like omega square a square sine square omega t. So that curve would look something like this. And when I add the two up, the sum would be a constant. Let me show it with red and blue together, and that's the total energy, half Ka square. So let me now sum up this introductory lecture on harmonic oscillator. In general, about stable equilibrium point, I would have, for small displacement about that point, an equation of motion like this. So the motion is simple harmonic, which is given like cosine omega naught t plus phi. The particle goes back and forth, or the system which has this kind of motion goes back and forth about an equilibrium point. The energy of the system is 1/2 Ka square, and the motion can be described by a Phasor diagram, which we will be using later in our analysis.